This lesson works through a center tapped full wave rectifier supplied by a 4040 volt RMS transformer secondary. We will calculate current, power, efficiency, regulation, peak inverse voltage and ripple factor. The important discipline is to keep the half secondary voltage, the conducting path and the chosen regulation convention clear at every step. The center tapped secondary is rated 4040 volts RMS. This means each half secondary supplies 40 volts RMS with respect to the center tap. Each diode has 1 ohm forward resistance. Its threshold voltage is taken as 0 and the load is 29 ohms. We must find the DC load current, DC load power, efficiency, regulation and PIV. On the positive half cycle of the upper half secondary, diode D1 is forward biased and diode D2 blocks. During the next half cycle, the lower half secondary reverses polarity, diode D2 conducts and diode D1 blocks. In both cases, the current passes through the load in the same direction. The output is therefore a full wave rectified sine wave with ripple frequency twice the supply frequency. At any instant, only one half of the secondary supplies the conducting path. Therefore, the applied RMS voltage for the current calculation is 40 volts, not 80 volts. One diode and the load are in series. So, the total conducting resistance is 1 plus 29 or 30 ohms. Transformer winding resistance is neglected. We first convert the RMS voltage of either half secondary to its peak value. For a sinusoid, peak voltage equals root 2 times RMS voltage multiplying root 2 by 40 gives 56.57 volts. This is the peak driving voltage available to one conducting diode load path with 0 threshold voltage for the conducting diode. The peak current is the half secondary peak voltage divided by the sum of diode forward resistance and load resistance. Substituting 56.57 volts and 30 ohms gives 1.8856 amperes. The instantaneous load current is the magnitude of a sine wave because its direction through the load is positive during both half cycles. For a full wave rectified sine wave, the average current is 2 over pi times the peak current. Applying this relationship to the calculated peak current gives 1.2 amperes. This average value is the useful DC component delivered to the load. DC power delivered to the load is the square of the DC current multiplied by the load resistance. Squaring 1.2 amperes and multiplying by 29 ohms gives 41.76 watts, which we report as approximately 41.8 watts. Rectification efficiency is useful. DC load power divided by AC power supplied to the rectifier load path. AC power must use RMS current. For a full wave sine, RMS current is peak current divided by root 2, giving 1.33 amperes. The DC power determined already is 41.76 watts and the AC power is 53.33 watts. Hence, the rectification efficiency is 78.3%. The idealized average no load voltage is 2 over pi times the half secondary peak or 36.01 volts. At full load, the average load voltage is DC current times load resistance, giving 34.80 volts. Using full load voltage as the denominator gives 3.48% regulation. If no load voltage is used as the denominator, the result is 3.36%. Always state the convention. When one diode conducts at a half secondary peak, the other diode is reverse biased by the sum of the two half secondary peak voltages. Therefore, The peak inverse voltage is twice 56.57 or 113.14 volts. This is only the theoretical minimum. A practical diode needs a comfortably higher repetitive reverse voltage rating to allow for line variation and transients. Ripple factor is the RMS value of the AC component divided by the DC component. Since total RMS current contains both DC and AC components, the ratio can be written as the square root of the squared RMS to DC ratio minus 1. Substitution gives 0.483 or 48.3%, the standard value for an unfiltered full wave rectifier. The completed calculation gives a DC load current of 1.2 amperes and DC load power of about 41.8 watts. The diode resistance lowers efficiency to about 78.3%. Regulation is 3.48% with the full load denominator. Each diode sees a theoretical PIV of 113.14 volts and the ripple factor is 0.483. Several errors are especially common. Do not use 80 volts RMS as the conducting voltage because only 140 volt half secondary drives the load at a time. Do not include two diode resistances because only one diode conducts. Use RMS current, not average current, for AC input power. For PIV, use twice the half secondary peak. State the regulation convention. Finally, choose a practical diode with reverse voltage margin rather than one rated exactly at the calculated stress. The center tap and alternate diode conduction produce a unidirectional full wave load current. The current calculation uses 140 volt RMS half secondary and one diode resistance. Average current determines the DC output, while RMS current determines AC input power. A center tapped rectifier requires each diode to withstand approximately twice the half secondary peak voltage. These distinctions lead directly to the calculated results and help prevent the most common design errors.